Let's solve problem 2.57 from Microelectronic Circuits 8th edition by Sedra and Smith. Complete the following table for feedback amplifiers using one ideal op-amp. Note that Rn signifies input resistance, and R1 and R2 are feedback network resistors. Let's draw an inverting and non-inverting op-amp and see if we can derive any formulas. So let's start with the inverting amplifier. So we usually start with a voltage source, which feeds into a resistor, which would be R1 in this scenario. It will feed into the negative terminal of the op-amp. Positive terminal will be grounded. We will connect R2 between the output and input terminals of the op-amp, followed by Vout, which will be grounded. We know that the gain is equal to negative R2 divided by R1, and that Rin, the input resistance, is just equal to R1. What about a non-inverting amplifier? Let's draw this in red. So we'll still have R1 connected to the negative output, a negative input terminal. However, this time, the positive input terminal will be connected to the voltage source. But again, R2 will still be connected to the negative input terminal and the output terminal. So we essentially are just moving the voltage source from the negative terminal to the positive terminal. And this makes the gain equal to 1 plus R2 divided by R1. What about Rin? Well, remember, for an ideal op-amp, we have infinite input impedance, meaning the impedance inside this positive terminal is infinite, which is where the voltage source is coming from. So therefore, it is infinite. Okay, so let's try to fill out this table. If the gain is positive, that means we're dealing with a non-inverting amplifier, which means that Rin is equal to infinity. So let's go ahead and fill those in. And let's go ahead and solve for R1 and R2 for all of the inverting op-amps. So for case D, notice how it's just 1 volt. Our gain is equal to 1 volt, which is equal to 1 plus R2 over R1. So essentially, R2 divided by R1 is equal to 0. Therefore, R2 has to be 0. And R1 should be equal to infinity. We can't just make it equal to 0 because 0 divided by 0 is an invalid mathematical expression. So it can really be any number greater than 0. But for this, I'm just going to go ahead and state it's infinity. Now for E, we have an actual value of R1. So we have 25 is equal to 1 plus R2 divided by R1. So we can state that 24 is equal to R2 divided by R1. So R2 is equal to 24 times 100 kiloohms. So that is R2 equals 2,400 kiloohms. Let me erase this and I will start solving the next few cases. All right, let's work on case F. So we have the gain is equal to 9. That's equal to 1 plus R2 over R1. We have R2, so we just need to solve for R1. So that's 8 equal to R2 over R1. Therefore, R1 is equal to 40 kiloohms divided by 8, which is 5 kiloohms. Okay, now let's drill back to case A. So you know that R1 is just equal to Rn, so that's equal to 20 kiloohms. The gain is equal to negative 10, which is equal to negative R2 over R1. So therefore R2 is equal to negative 10 times negative R1. So that's negative 20 kiloohms. So R2 is equal to 200 kiloohms. Okay, let me erase this and we'll keep going. All right, let's move on to case B. We know that Rn is just equal to R1, so that's 100 kiloohms. We have the gain is equal to negative 4, which is equal to negative R2 divided by R1. Therefore, R2 is equal to negative 4 multiplied by negative R1, which is 100 kiloohms. So that is 400 kiloohms. Now for case C, we have R2 and our gain, negative 2, which is equal to negative R2 divided by R1. So R1 is equal to R2 divided by the gain. So that is 20 kiloohms divided by 2, which is 10 kiloohms. And again, Rn is just equal to R1, so it's also 10 kiloohms. Okay, let me erase this and we'll do our last case. Okay, let's wrap this problem up with case G. We know that R1 is equal to Rn, so that's going to be 10 kiloohms. We know G is equal to negative R2 divided by R1. So therefore, R2 is equal to negative G R1, which is equal to negative 0.5 times 10 kiloohms. So R2 is equal to 5 kiloohms. And we have completed the table.